Imagine you're driving a self-driving car when a sudden snowstorm blurs the road. The AI must adapt instantly, but how does it know if its decisions are still reliable? This is the crux of Test-Time Adaptation, TTA, a revolutionary AI technique that lets models learn on the fly. But here's the catch. Even the smartest systems can falter if they lack a built-in safety net. Today, we're diving into how researchers are keeping AI safe during real-world shifts, without human intervention. TTA is like giving an AI a cheat code. Instead of relying solely on its training data, it tweaks itself using new, unlabeled information from the real world. Think of it as a student who studies during exams, not just before them. But here's the problem. If the environment changes drastically, like snow obscuring cameras, the model might start making errors. And in high-stakes scenarios, that's not just a glitch, it's a crisis. That's where risk monitoring comes in. It's the AI's equivalent of a dashboard, not just showing where it's going, but warning it if something's wrong. The researchers behind this study developed a framework that tracks a model's performance in real time, even when there's no labeled data to guide it. How? They used sequential testing, a method that constantly checks if the model's predictions hold up. Here's the magic. They paired this with confidence sequences which act like dynamic error bars. Imagine a weather app that updates its forecast as new data comes in. These sequences adjust in real time, telling the model, hey, your confidence is dropping. Something's off. This means the system can flag problems as they happen, without waiting for a full dataset. But here's the real breakthrough. This system works without labels. In most AI setups, you need labeled data to detect issues. But in the real world, labels are rare. The researchers solved this by focusing on the model's uncertainty, how confident it is in its own predictions. If the model starts doubting itself, that's a red flag. It's like a doctor noticing their own hesitation during surgery. Something's not right. And the results? Their tests showed this system reliably catches when a model is failing, without false alarms. It works across different types of data shifts and adapts to various AI models. This means safer, more reliable AI in the real world, whether it's diagnosing diseases, driving cars, or managing climate systems. So what does this mean for the future of AI? It's not just about making models smarter, it's about making them safer as they evolve. And that's a game changer. Thanks for watching. If you want to dive deeper into how AI learns on the fly, hit subscribe. Stay curious and let's keep pushing the boundaries of what machines can do, responsibly. Let's break it down. When AI models adjust to new data, like a camera learning to recognize objects in rain or snow, we call this test-time adaptation, TTA. But here's the catch. How do we know if the model is still reliable? That's where monitoring systems come in. They act like a dashboard, alerting us if the AI starts making mistakes. The big question: how do we make sure these alerts are accurate? No false alarms, no missed dangers. The research we're exploring tackles this with a clever statistical trick, an unsupervised alarm that doesn't need labeled data. This is huge because real-world data is often messy and unlabeled. The alarm, called 5T, uses a probability of false alarm, PFA, guarantee. Think of it like a security system that promises false alarms stay below a set threshold, even as the model adapts. Here's how it works. Under the assumption the model is behaving normally, the null hypothesis, H0, the researchers prove the alarm only triggers if performance drops significantly. They use confidence sequences, a way to track risk over time, with tight bounds to ensure reliability. For example, if the AI's accuracy plummets, the alarm goes off. But if it's just fluctuating normally, it stays silent. But what if the model starts struggling? That's where H1 reactivity comes in, the system's ability to react quickly to real issues. Traditional methods often miss problems by being too conservative. The researchers solved this by comparing two types of errors. 1. Binary errors, yes-no, like a light switch, correct or incorrect. They tightened monitoring bounds here, making the alarm more sensitive. 2. Continuous errors, like a dimmer switch, measuring how wrong a prediction is on a scale. They introduced a trick, comparing the model's current performance to its past behavior using the same threshold. This helps catch subtle drops in accuracy faster. They also tested their method against popular approaches, like using energy scores to detect errors. While those work, their method using model uncertainty, a measure of how confident the AI is, produced tighter, more reliable bounds. It's like switching from a basic thermometer to a high-precision sensor. Smaller margins of error mean better warnings. And here's the kicker. Even with a small dataset, their method performed almost as well. Think of it like a car's sensors. You don't need a massive test track to know something's wrong. So next time you see an AI adapting to a new situation, remember, it's the result of decades of research, a dash of creativity, and a whole lot of problem solving. Stay curious, and let's keep exploring the frontier of machine learning together. What's clear is that TTA is no longer just a lab curiosity. It's a critical piece of the AI puzzle. By learning on the fly, these systems are becoming more resilient, adaptable, and trustworthy. And as we continue to push boundaries, the future of AI looks not just smart, but safely smart.